if you look at question 1, I believe you guys are able to see clearly what struggles. So this is last year's paper. Consider the half reactions and their reduction potentials. So we've been given the reduction potentials. Now, quickly, looking at the way these reactions are written, what do you think? Are these reduction reactions, or they are oxidation, or it's both? Okay, reduction because they are all involving what? Gain of electrons, just like our friends defined reduction. Okay, so in this case, we want to come up with a redox reaction. So one is supposed to be reversed and become an oxidation reaction. So which one are we going to reverse? Is it the first one and the second one? And give us a reason why. Why are we reversing the first one? Okay. So the basic idea is what we want is each time we're dealing with these, we want to get a positive standard cell potential for the galvanic cell, right? Positive standard cell potential. We always want to be positive. Now, the basic idea is we do understand that when we reverse, we need to add the 2. So as we get to reverse, the sign changes. So if I reverse the first one, the sign will become negative 1.47. Now if you add the 2, are you going to get a positive value or a negative value? A positive value. Now, what if we did the opposite? Would it still be positive or negative? Okay, to be a negative value. So this is the question that I was receiving the other day to say, isn't the formula for calculating the standard cell potential, is it like the cathode and then subtract, is it the anode? Is this the formula that you use? Yeah, someone was asking me this question on YouTube, that is. So the basic idea is this negative applies to a case where you don't reverse and then you're just trying to perform calculations directly, right? So that negative is the same as changing the sign for our anode because we are making it the oxidation reaction. So don't make a mistake of reversing and then putting a negative there and then you come and again subtract. That's wrong. So to avoid those confusions, all I just say is just add when you're calculating the standard cell potential. So that would require you each time to reverse the oxidation reaction. So in this case, we're going to reverse our first reaction as we've been guided. So I don't have to do that. You can do that. Now, the question says give the overall cell reaction. So if we reverse, these are going to be on the left. Okay? And then this group will be on the right hand side. So we know what are reactants and what are products. So to write the overall cell reaction, we need to balance first of all the number of electrons to start with. Now look at the number of electrons that we have in the second reaction. We have got 2 electrons. There we have 10. What do we do? Multiply by what? What should we do? Multiply by? Okay, good. So that we balance the number of electrons. So 5, it become 10, 10. Okay. So our reactants, we have this part plus that part. So the electrons will cancel out because we know this side is moving to the right hand side. Okay, does that make sense? So the electrons will cancel out. Remember I've said reverse the first reaction there. So on our reactants part, we have this part plus what is on the bottom there. So we have others say no, start with the anode and whatnot. I don't see any difference, but we can do that. So chlorine 2 plus 6 water molecules plus 5 S2O2. Oh, it's 8. O8 2 minus, and then our products, we have this plus the other 2. So we have 2 chlorine, 3 negative plus 12 hydrogen ions plus this guy, 10 of it. So I don't have enough space. I was just guiding you. I believe you know how to go about that now. Just reverse, add the reactants together and the products together, come up with one reaction. That's how you come up with your overall cell reaction. So the basic idea is you want to reverse the oxidation reaction, because usually they'll give you reduction potentials. Calculate what? The Gibbs free energy of the reaction. Given that, so this was an omission. I don't know if it's standard cell potential or something. So what happens if you perform the calculation there? That is negative, add with 2.01. What is the answer? You guys. 0 point. So you've given us the answer for us. In a normal case, we are supposed to ask you to calculate and then use it yourself. So standard Gibbs free energy is equal to negative. I'm trying to remember this formula. N denotes what? N denotes what? The number of what? So are we using 10 or using 2? So you use the balanced number of electrons. Okay. So in a case if we had, like, let's say 3 electrons on top, we can't say we're going to go for the 3 electrons. We'd have to balance, and we can only balance by multiplying the top part by 2, the other one by 3. And again, I'm trying to emphasize on this part because what we basically do under S's law, whatever we do to the equation, we do it to the enthalpy. But the standard cell potential is not affected by what you multiply the equation with. That's very important. Okay, don't mix up the data. So here we don't whatever we multiply the entire equation doesn't affect the standard cell potentials. Very important. So we have 10. Faraday's constant is always given in the paper, which is what, 96? Is it 96? I'm not getting what you're saying. What are you saying? Do you have a question or you're contributing? Okay, so guys, am I the only one who is not able to get her? Okay, what about the number of electrons, madam? What can we do for you? Okay, maybe she has a slow network, so she can catch up. So the number of electrons are 10. Faraday's constant should be 96485. It's always given in the paper. And then the standard cell potential has been given for us. Now Gibbs free energy. What are the units for Gibbs free energy? What? Okay. So we know that a positive standard cell potential denotes a spontaneous reaction. A negative gives free energy, denotes a spontaneous reaction. So these two guys are going to be opposites. Are we together? Make sure you take note of that. Okay, move to the next question. Positive standard cell potential denotes a spontaneous reaction. Negative gives free energy, denotes spontaneous reaction, implying that when your standard cell potential is positive, you do expect that your Gibbs free energy should be what? Negative. That's why we add a negative to the formula. This is another question. A Voltaic cell is based on the following. So we were given two F reactions. This is the use of a Nernst equation. What do they want us to do? So we are saying the conditions in the cell were temperature 25. The concentrations were given. Calculate the cell potential, calculate the reaction quotient, draw a fully labeled cell diagram of this Voltaic cell. Okay, as simple as it is. They want us to answer this simple question. So what do we do? So first of all, we need to understand that in this case, if you observe the concentrations that we have, these are non-standard. This is non-standard cell potential what we're trying to calculate. Looking at it, the other way we can reason is by looking at the concentrations. The standard conditions are that at equilibrium, the standard conditions are that we need to have 25 degrees Celsius as we're given, or it can be given in kelvins, 298, which is the same if you add 273 to the 25. And then the concentration is supposed to be 1 molar concentration, the pressure is supposed to be 1 atm. So those are conditions those are the standard conditions. Now in this case, look at the concentrations that are given. They are non-standard. 2 molar concentration, all these. So that's why we are calculating a non-standard cell potential. So we calculate the non-standard cell potential by using the Nernst equation. Okay. Let me just do this. Are we on the same page? Okay, so hopefully you're able to see the question so that I answer it. The next equation is, I hope I'll be able to remember it. The what's the equation? So the non-standard cell potential should be equal to the standard cell potential minus, so at 25 degrees Celsius, the formula is direct to 0.0591 divided by n log of Q. Is that fine? Or I've swapped the standard with non-standard? Okay. So the full formula is RT, this part is RT over number of electrons and the Faraday's constant. At equilibrium, what do we know at equilibrium? Any comments? What happens to this formula at equilibrium? Okay, so Q becomes K, as we've seen from our study under chemical equilibrium. We've seen that K denotes equilibrium constant, Q denotes the quotient at any point in the reaction. So at equilibrium, the standard cell potential, the non-standard is a 0. So this one usually goes the other side, so that we get to generate a simple formula that is standard cell potential is equal to 0.0591 over n log k. So these are the cases where they'll ask you to find k. Okay, so make sure you familiarize yourself with these two forms of equation. So if you know one equation, know the conditions at equilibrium, you are good to go. Okay, so we need to now look up the information that we need. We need the standard cell potential, which we were just from talking about. And without wasting much of your time, if you look at, are you able to see first of all the question? Is it visible enough? So they want us to find first of all the standard cell potential, not they want us. The equation tells us so. So if we look at the number of electrons, they are already balanced. Now which side are we reversing? Are we reversing the top part of the second equation? Give us a reason. Okay, so thank you, sir. We always reverse the smaller one. Thank you very much. That is a simple statement we can use. So we'd have to reverse zinc, implying that zinc would have to get oxidized. It has to be on the anode part, so that it becomes 0.7 volts. In this case, they are not interested in our equation, so we'll just go on and just like determine the standard cell potential by adding the two values, which I believe 1 plus 0.7 will give us 1.70 minus 0.0591. The number of electrons are already balanced. I believe it's a single electron. If this, yeah, single electron, and then log Q. So now some of you are already asking a question, log Q. So that's why I feel they need to start teaching equilibrium before you learn electrochemistry, because it is very important to understand what the Q and the K are. Okay, is that okay? So we understand how to find the Q. Whenever we're finding Q or K, we always use aqueous states. Everything else, solids, liquids are ignored. We only use gaseous and aqueous states. So in this case, for us to understand basically what is going to happen, it would have to require us to write now the overall equation again, which we wanted to ignore. Okay, let me just do one more tactic here, just to help us to work well. So just do this. Okay, much better like that. So we'll write the equation. So we've reversed the second reaction, implying that this part goes the other side. So that we have zinc 2 plus an electron. So we'll combine the reactants. So for the reactants, we have, I'll start with the anode. So we have zinc solid plus what is on top, VO plus 2 hydrogen ions. The number of electrons have cancelled out, and then we have zinc 2 plus VO2 plus. This is the only problem with the Dafroid's documents and whatnot. I believe this is an error. Who is able to observe the error that is here? So there's supposed to be a difference between the two. VO2 plus. Okay, let me just look over that. Just a second. So we have water on our right hand side. So on the right hand side, wait. Let me check again. Let me check. Okay, is anyone able to help me with what is supposed to be shown there? Is the equation fine as it is? Oh, I'm just overthinking. Okay, so supposed again. This is too confusing. Let me see. Okay. Okay, so it's supposed to be VO on the right hand side. There's not supposed to be subscript 2 there. Okay, I don't know if it becomes balanced now. So it's supposed to be VO plus. Okay, I hope we're on the same page now. Sorry for that. Yeah, so what was the difference? That was supposed to be, that's not supposed to be there. Yes. So we have just VO, not VO2. I doubt if a charge is supposed to be there. Okay. So this is the full equation now. It was necessary for us to come up with that equation because as we look at our Q, as we know each time we are trying to find the quotient Q, okay, we need to divide the products by the reactants. So look at the given information. Which ones are products? So let's identify the products. We have zinc 2 plus, we have VO and water. Now water is in liquid state, we can't assure it. Okay. So what do we have as a piece of information? So we have V. This is going to be tricky. So zinc 2 plus is there. What else? Our VO, where is it? It's here. So 0.01. So it was supposed to be 2 plus. And then our VO2 was our reactants. So we'll go by our products. So we have zinc. I'll write the answer. It was 0.1 multiplied by the other product, which is VO, 0.01. So these are supposed to be raised to their coefficients. So they all have coefficient of 1s. On our reactant side, we have hydrogen, which has been given to be 0.05. So it's supposed to be the power 2 because of the coefficient. And then what else do we have? We have VO2 plus, which is 2 the power 1. So notice that zinc will not appear because it is a solid and no information has been given about it. So with that piece of information, I believe we are now able to find our value of our Q. Any questions there? Questions? Okay. Okay, if we understood. Go on. Just repeat that. Yes, it's the same way. Okay, I've answered your question. So the value of Q, how do we calculate there? Anyone who has already calculated everything, we just like write the answer. No one. There's no good Samaritan. So remember, in case you've forgotten, the formula was E is equal to E standard. Okay. So I'll take back the question there. So our value of Q is supposed to be there. Now I'm waiting for you guys to calculate there. What's the answer? No one knows. 0.1 multiplied by 0.001. So 0.001 divided by 0.5 squared is what? Times 2. 0. What? 2 zeros and 5. Okay, 0.05 like that. Okay. And then if you get to divide the two, what's the answer? 0. What? 0.2. So we found the value of Q. That was necessary and essential. So my advice is, in this case, simplify what is this side. So 0.0591 0.0591 log 0.2. The good part is we don't have anything to divide by. So whatever you get, divide by what is on the bottom, which will remain the same. So I'm having negative 0.04. Just confirm my answer if you get, because I'm using a phone yet to just calculate that. And then it will become a positive now, which will give us what? Repeat that. 0.741. Okay. Now looking at the number of significant figures given in the question, the least number of significant figures we have, how many do we have? What's the least number of significant figures in the question? We can't say. How many significant figures are in 0.1? Hmm? No one knows. How many significant figures are in 0.1? How many significant figures are there? Okay, so what is the answer? What answer are we going to write? Excuse me? Okay. This is against their rules, but more preferred to write that than to round off. 2.0 is two significant figures, but why would you round off again? So calculate the reaction quotient. So we've just calculated the reaction quotient Q. That's what you put in the second part as well. So the possibility is, okay, I don't see the point of asking reaction quotient after the standards, after a non-standard. But anyway, we've already found the Q, so that's the answer demanded for in the second part of the question. Draw a fully labeled cell diagram of this Voltaic cell. A Voltaic cell is a galvanic cell, so we all know how to do that. What is important is our equation that we've come up with, telling us to say zinc is the one that is on what? The anode, because it was reversed. Okay, so we'll be careful on our electrodes. We'll put our metals here. We have zinc, right, in solid state. The other side, do we have anything in solid state? We don't have anything in the first reaction, so we'd have to use platinum. We can put a cathode bridge here. What else? What is going to be in solution? For our zinc, for our anode part, we're just going to put zinc 2 plus ions. The other side, we'll put everything else, because everything else is in what? Is in aqueous state. So VO, all the reactants and all the products. Including the hydrogen ions. Yes, sir. Unless if you have a different view of what the reaction quotient is. Yeah, so reaction quotient is Q itself. Okay, so we are done for this question, which I believe has helped us revise the Nernst equation. This question I've done you a favor by just sending the solutions. I'll send the solutions to the group immediately after the class. All these questions have been answered, well explained. If you get stuck, you can get back to me. Let me. What brief explanation is going to be there? It's a very simple part. This is a galvanic cell, sir. So there's nothing new about it. All we are doing is identifying what was missing. Is this a galvanic cell? Yeah, it is. So a diagram shows a cell that can be used to measure the standard electrode potential of the earth reaction. That in this cell, the electrode on the right hand side is positive. So is hydrogen gas shown there. Identify solution A and give its concentration. State one other essential condition for the operation of a standard electrode from the left hand side of the cell. Now what have we observed there? We've observed production of bubbles. Why do we have a production of bubbles? Any ideas? Let me just add these people again. Okay. So without wasting much of your time, when you look at the question A there, we are asked to identify A and give its concentration to start with. So looking at what is being produced, we have bubbles being produced. Okay. What have we seen? We've noticed that hydrogen is being added. Okay. So what happens? So the possible solutions that we can have any acid there. Okay. Any acid can be allowed. Of course, we can have sulfuric acid, and then we can also have nitric acid. Okay. So what is necessary or what is important is, or even hydrochloric acid itself. What is important is you being able to understand the mole ratios, because they need that as we get to observe and give its concentration. So if you write a reaction between hydrogen and is it possible for hydrogen to react with an acid? What do you think? Is it possible? It's not a possible reaction. Okay. So looking at the production of bubbles, I believe we can think of it as though the hydrogen gas is what is being produced. In such a case, we would have a reaction between hydrochloric acid and what? So if you have a reaction between hydrochloric acid and water, what gets to be produced in such a case again? Do we feel that's a reaction that is taking place? Okay. So we'll take it as it is. Let's not be interested in the reaction that is going on there. What is going to be necessary for us is to just identify what is being on the anode and what's being on the cathode, and also the production of electrons going the other side. So the possible reactants here would be the acids there. Okay, so hydrochloric acid is one of the possible solutions, sulfuric acid, and also nitric acid. And then for these ions, these acids that have got a single hydrogen, the concentration would be 1 molar concentration. For sulfuric acid, the answer is supposed to be half of it. Okay. So we can think of it in this way again. We can think of a single reaction of hydrochloric acid itself getting to react to give us hydrogen and the chloride ion. Identify or state one other condition for the operation of a standard electrode that forms the left hand side. So the other necessary condition is that the hydrogen that is being used is supposed to be at 1 bar. I don't know the conversion factor from, let's not talk about complicated units, we can work with what we know. So 1 bar is basically equivalent to 25 degrees Celsius. So this is supposed to be at standards, or you can use kelvins, 298 kelvins. I believe that is more friendly to most of us. Identify the material from which electrode B is made. So the idea is, as we've observed, we're working with acids and a gas here. So these guys are not capable of giving us an electrode. So what basically happens, we can use non-reactive metals. So platinum is one of them. And then they are also saying give 2 reasons why this material is suitable for its purpose. So we can use platinum because it's unreactive, and then it's also capable of conducting electricity. So not only should we get something unreactive, but it should also be a metal so that it's capable of conducting electricity. And then identify a solution that could be used in C to complete the circuit. So in C, that is the salt bridge. What can you use? Yes? Remember what we are using here is if we have put hydrochloric acid there, what can you use? Sodium chloride. Sodium chloride is fine. What else? So it's potassium what? Potassium chloride. Is that the way you write it? That's fine as well. Okay. Now I believe there should be a follow-up question as well. Should be 29. Oh, 25 degrees Celsius or 298 kelvins. Okay. Yeah, so the other questions you can still look at the solutions that I'm going to send. Reasons like why the ammeter reading would fall to 0 after some time. All those questions are answered. I don't think so. Is there any need for us to spend time on this question? Okay, let me just give an explanation on it. So we've been given the full reaction itself, redox reaction. Now we've said the standard cell potential has also been given. They've given us the reduction potential of bromine. Now what do they want? They want us to find the reduction potential of the other reactant. So what do we do? So look at this guy. So bromine being reduced to that has got that. Okay. So do you feel bromine in this case is being reduced or it's being oxidized? What do you think? Is it being oxidized or it's being reduced? It's what? It's being reduced. Okay, interesting. Then do you think this one is being reduced or oxidized? Hmm? So which one do you think is more capable of reacting with water as a half reaction? Is it bromine or the other one? Okay, so try to look at your table for the half reactions. Okay, so we have V2 plus here, we have 2 V3 plus. So in terms of half reactions, it is possible for us to just have this as it is. Since it's in ionic form, we can consider this one to be as basic as it appears to be, just as it is, going to give us the other parts. So in that case, we'd have to agree to say that is a reduction half reaction. We were moving from 3 plus to 2 plus. And then since this one is not necessarily in ionic form, so we can consider this one plus water to be the same reaction, giving us hydrogen plus that. So in that case, it becomes what reaction? So we can combine the 4 plus the 2 minus. We have 2 plus on the right hand side, and then on the left we have got a 0. So that is oxidation reaction. Okay, so now we do understand that our standard cell potential is basically the addition of the anode and the cathode. Of course, we need to take note that the anode is supposed to be the reversed one. So after reversing, it becomes a negative. So we'll put minus A for the anode. The cathode, we've already been given the value to be 1.07. The standard cell potential has been given to be 1.39. So we can take A the other side so that it becomes positive. And then we have the addition of 1.07. Do we have the addition or the subtraction? 1.07 minus 1.39. What answer do we get there? Negative 0.32 volts. Okay, so that is fine as our solution to that question. Okay, is the reaction spontaneous or not? Yes. Okay, so we find the standard cell potential by adding the, or whatever formula you are used to. You can say your standard cell potential is your cathode minus your anode. So the standard cell potential has been given. So which one is your cathode? So we've identified this one to be a reduction. So it is supposed to be on what? Reduction occurs on the cathode, right? And the value has been given to be 1.07. So 1.07 minus the value of A we don't know. The standard cell potential of the reaction has been given to be 1.39. So we just like make A the subject. That's how we got that part. Is the reaction spontaneous or not? Just look at the value, the sign of the standard cell potential. You don't have to think, you don't have to calculate. Okay. So now as a good student, I believe you know how to write that. They can ask you to write the cell notation like that. Okay. So familiarize yourself with it. You can even go to Moodle. There's a video about that, in case you don't know. And then this is one of the questions where the solutions I'm sending to the group. If you not understand, you can get back to me. Obvious questions from what we've talked about, you're able to answer them. Okay. So try attempting all these questions. Now I believe this is a question that our friend has sent in the group. Now looking at the time, I don't know if we can continue, but I believe most of you are already tired. So I'll post a video. Yeah, I'll post a video just soon after. And then you can watch it. If you not understand, we can talk about it as we conclude our class tomorrow on phase equilibrium and the other part that has remained.